So start with the problem number 2. In this problem, we have to draw shear force and bending moment diagram. There is a beam which have a span A and B. The total length of the span is 16 feet. Till 8 feet, we have a uniformly distributed load of 800 pound per foot. And we have a point load at far end at point B, which is 1200 pound. And we have to draw shear force and bending moment diagram. Also, the value of x is missing, so we have to calculate the x as well. So proceed with the whiteboard so we can draw shear force and bending moment diagram. To calculate reaction, first of all, we have to make the free body diagram and then we will proceed accordingly. So to draw shear force bending moment diagram, we have convert this UDL into point load. So initially it is 800 pound. So 800. Yeah, so this is 800 times total distance is 8. So it is 6400 pound. Okay, the point is, and it is acting at a distance of, because the total distance from here to here is 8 feet, and from here to here it's 8 feet. So this is 8 feet, this is 8 feet. So it will be from here to here 4 feet. You can say C, A, and B. So the magnitude of this one is 1200 pound, and this is unknown. So here we have a fixed support, so we have a support reaction movement as well, and AY. So here we have AY and movement at A. Okay, and movement at B equals to 0 because there is no support. And so that's it for the free body diagram. So now we have to determine the support reaction. First, do the summation of movement at A is equals to 0. That is a movement created by this 1200. So it will be clockwise. So take it anti-clockwise positive. So minus 1200 into what is this thing? 16. 16 minus 6400 into 4. 6400 into 4 and plus MA. We assume that anti-clockwise movement at A. So MA will be, after calculating, will be 44800 pound feet. Okay, pound feet. Okay, now summation of forces in the direction of Y is equal to 0. So AY upward positive minus 6400 minus 1200 is equals to 0. So AY will be 7600 pounds. Okay, so this is the value of AY, 7600 pound, and this is the value of movement at A, 44800 pound feet. Okay, now we have to draw shear force and bending moment diagram for the following figure. Okay, so to draw shear force and bending diagram, we have to put all the values here. That we have UDL here, and from here to here we have a UDL of 800 pound per foot, pound per feet. Okay, and anyway, there's some problem in the pen. Anyway, so 1 minute. Okay, we have a load of 800 pound per feet, and here we have support A, here we have support B, here we have support C, we have point C, and now this distance X is unknown. Okay, this is the figure. Now here we start from the 0 point, and AY we calculated as 7600 pound, and movement we calculate anti-clockwise 44800 pound feet. Okay, so start from the shear force diagram. So here to here we have a UDL. We start from the zero line. So first we have upward force of 7600. It's here. Then we have you can say that we have the UDL from this point to this point. Okay, so we have to and which is acting downward. This is acting downward. So we have to subtract the area of this UDL from this. So what is the area of this UDL? It's 800 multiplied by 8, which is 6400. So the equation will be 7600 minus 6400. It will be 1200 positive. So it will be above this. So we just draw a one line from here to here. Okay. Then we have from here to here, there is no load, there is nothing. So from here to here, we have a center straight line. And then here we have a point load of 1200 pound downward. So this is 1200. This is 7600. This is 1200 as well. And there is a load of 1200 pound downward. So it will be 0. So the shear force diagram is both positive and it closes at 0. So this is triangular body and rectangular body, positive zone, and it is just a rectangular body. Okay, so this is a shear force diagram. Now time to calculate the moment. For moment, we will calculate the we will start from the 0 usually, but there is a fixed support, so we will start from 44,800. Okay, we will start from 44,800. This is our first moment. Keep one thing in mind, that when we have the when we have no load, or the point load, we will use first degree line, like straight line, first degree line. But when we have any load UDL or varying distributed load, that is VDL, so we will use second degree of line, that is a curved line. Okay, always remember this thing. So now we have to draw bending moment diagram for this figure. So to do that, we have to add or subtract the area under the shear force diagram. We start from 0. If we start from 0, we will add this area under the shear force diagram, and then we will start from 0 line and make a line. But here we already have a moment, so our equation will become like this: minus 44,800 plus area under this under this figure. So here we have actually two identical bodies. Okay, now you can see here, if I zoom it, this body is like this. So here we have one square, a rectangle, and one triangle. So from here to here, the value is 1200, and from here to here, it is 7600. 7600. So what is the value from here to here? This minus this, like 7600 minus 1200 is equals to 6400. The value I'll represent with the red line. The value from here to here will be 6400. Okay, so we have two bodies basically. This is one rectangle body and two triangular body. Okay, now we have to make area for both the bodies. So the distance from here to here is 8 constant for both the bodies. So for this body, it will be 1200 into 8 plus half time AB. Oh, A is 6400 into 8. Why? Because area of triangle is half AB. Area of a triangle is, suppose this is a triangle, this is A, this is B. So area of triangle is half AB. So in our case, A is suppose 8 and 6400 is B. Okay. So we just make it like this. So it will be, when we solve this one, answer will be minus 9600. So it is below the 0 line. So we will put it here minus 9600 and make a second degree curve because it is a UDL. Then we have to add area of this one because it is positive. So our next equation will be, I'll clear this one. Our next equation will be minus 9600 plus 1200 into 8. So it will be 0. So we will close our bending moment diagram at 0. Okay. So this is both in negative zone. Both in negative zone. So our bending moment diagram here in the negative zone. So this is shear force diagram and this is bending moment diagram. Start with the problem number 3, in which we have to draw the shear force and bending moment diagram for the following beam. So there is a beam here. You can see that there is a beam in which we have 2 kip per foot. We have a load UDL and till point A. So there is a roller support. There is a roller support and there is a hinge support, and this is a continuous beam, and this is cantilever. Okay, and here we have a moment of 30 kip per foot. Okay, so first of all we have to make a free body diagram and start calculating the support reactions. So this is our shear, free body diagram. Okay, now we will start calculating support reaction. First, we have to calculate summation of forces in the direction of y equal to 0, upward positive. Okay. So here we have how it 10 came, because we have a UDL of 2 and a distance of 5. So it is 2 times 5 equals to 10, and it is start acting at a distance of 2.5. Okay. Now we have to calculate summation of force in the direction of y. AY plus BY minus 10 equal to 0. Okay. Now summation of moment at A is equal to 0. So how many and anti-clockwise positive? So 10 times 2.5, it is positive because it is creating anti-clockwise movement at support A. This is A, this is B, and minus 30, what is 30? This is given clockwise movement. Okay, plus by time 10. By time 10. So from this equation, we can get by is equals to 0.5 kip. put the value of by in the equation number 1. You got ay is equals to 9.5 keep. Okay. So now we have a y 9.5 and by 0.5. Okay. So time to draw shear force and bending moment diagram. So for bending moment diagram, we have to make a beam, original figure. Here we have a UDL. Here we have a support at A, roller support. Here we have hinge support. Okay, here we have a moment of 30 kip fit, and the distance from here to here is 5, 5, and 5. Okay. So we have to draw shear force bending moment diagram here, 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 and here. Okay. And for shear force, let this a color. So this is shear force. This is shear force, and this is bending moment. Okay. Now we start from the values. Okay. Here we have, right now we have 0 value here. So from here, what is the value of ay? It was 9.5. Ay was 9.5 and by was 0.5, and this is 2 kip perfect. Okay. So from here, let me change the color so it will be easy to understand. Okay, green color is fine. So now from here, start from the 0. From here to here, we have a load of 2 times 5, and which is acting downward. So it is below the 0 line. So it is upward positive, downward negative. This is shear. Okay, so 0. Okay, from 0, it is 2 times 5 minus 10. So 0 minus 10 minus 10. It is from here to here. Okay. Then we have a upward force in the direction of like at A, we have a upward force 9.5 magnitude. So minus 10 plus 9.5, it will be 0.5, negative 0.5. So we just make a line from here to here. Okay. Now the value here is, here it is minus 10 and here it is minus 0.5. Then from here to end, there is no load. So we will make a straight line. So there is no load. So we will make a straight line because there is no load there. So from here to there, there is a straight line. But when they reach it here, it will experience an upward force at By. See, this is upward force at By. So we will use it and close it for the 0. So in this way, this is 0.5 negative and upward 0.5, it make it 0. So in this way, our figure is closed. But fortunately or unfortunately, all the values are in the negative zone. So this is negative, and this is negative. Now we have to make shear force bending moment. Bending moment diagram. For this bending moment diagram, we start from 0 because this support is cantilever, not fixed support. So we will start from 0. Now we will add area under the shear force diagram. So this is area under the triangle. So it is 5. So it will be half time A and B. In this case, half time 5 into 10, but negative. So it will be negative 25. And it is under the UDL. So it is a second degree curve. So it is negative 25. Okay. Then we have to, this is negative 25, then we have to have, one minute, make it big, slightly up so it will be easy. So this is negative 25. Then we have to minus this area because it is in the negative zone. What is this area? This area is 0.5 into 5, but negative. So negative will be positive, will be add. These two values will be add. Negative 25, negative 2.5. It will be 27.5 negative. So it will be 27.5 with a straight line. Okay. It should be straight line and it should look a straight line. See, we will just take it from here. So make a straight line of 27.5. So the value here is negative 27.5. Then we have a moment which is positive 30, because if you remember, we said that in internal coupling moment, we will consider it as a positive. If you remember our assumptions in the beginning. So 30 positive minus 27.5 will give you 2.5 positive. So it will come here. The value will be here 2.5. Then you have to subtract this area 2.5 minus 5 times 0.5. So it will be 0. And we can close it at this point. So this is our negative body and this is our positive. So this is shear force and bending moment diagram for the problem number 3. Jump to the problem number 4. In the problem number 4, we have to draw and shear force bending moment diagram for the following beam, in which we have a continuous beam. There's a support A and roller support at B, and we have a continuous cantilever. This is cantilever, but here we have a load of 6 kilonewton per meter, uniformly load distributed. The distance from support A to B is 4, and for support B to cantilever is 2 meter, and X is unknown. Okay, now we have to draw shear force bending moment diagram for this body. First of all, we have to draw free body diagram to calculate the support reactions. So just make it. Here we have UDL of 6 kilonewton. Per meter. Here we have a AY. Here we have, sorry, this is for the previous figure. So here we have AY. Here we have BY. Okay. The distance here to here is X, which is unknown. This is 4 meter. And this is 3 meter. So we can convert this UDL into point load by 6 into 7. It is total. Oh, this is 2 meter. So it will be 6 into 6. This is 2 meter. So it will be 6 into 6. It will be 36. And it will be act at a distance of 36 kilonewton. It will be act at a distance of 3 meter from here. Okay. Now calculate support reaction. Summation of moment at A is equals to 0, anti-clockwise positive. Okay. Now BY into 4 times BY minus 36 into 3 is equals to 0. This is a moment created by these two forces at support A. So BY will be 27 kilonewton after calculation. Then summation of forces in the direction of Y is equals to 0, upward positive. So it will be BY plus AY minus 36, where by is 27, ay is equals to 36 minus 27, it is 9 kilonewton. So ay is calculated. Sorry, ay is calculated. So we know ay is equals to 9 and by is equals to 27. Okay. So far, so good. Now we have to draw shear force bending moment diagram. So now draw shear force and bending moment diagram. Start from 0. Okay. So this is shear force, positive upward, negative downward. Okay. Now we know ay is 9. So we start from this point. Our value of a is 9. 9. Okay. So from here to here, it experiences a load of UDL load of 6 kilonewton per meter. So this is 6 kilonewton per meter. So equation will be like this: 9 minus 6 into 4. It will be 9 minus 6 into 4 is equals to minus 15. So minus 15 will be like this, will be minus 15. So minus 15 will be somewhere here. So if we draw the value, this is minus 15. Okay. Then here at by, we have a upward value of 27, which is upward 27. So minus 15 plus 27, it will be 12. Will be 12. It is somewhere here. Okay, 12. Then from here to here, it will experience 6 times this distance. This is 2. So 6 times 2 is 12. So minus 12 will be equal to 0. So it is 0. Okay. We know the distance from here to here is, this is 0. We know the distance from here to here is 2. This is, from here to here is 4. But from here to here, it is unknown. The point where it is crossing, it is unknown, which is x actually. Okay. It is actually x. So we have to determine the value of this x. Okay. Suppose now, see it very clearly that how we calculate the x. Okay. Now from here to here, what is the distance? 4. Okay. From here to here, it is 4. So, and from here to here, it is x. So what is the distance from here to here? Is 4 minus x. Total minus this distance is this distance. So this is actually 4 minus x from here to here. Okay. From here to here, it is 4 minus x. Okay. This is x, which is from here to here. Okay. So now we have two triangles. This is one triangle, triangle number 1. This is triangle number 2. So using the method of equal triangle, 9 over x is equals to 15 over 4 minus x. Okay. 4 minus x is this distance. 9 over x is this distance. Okay. So it will be 9 is equals to 4 minus x is equals to 15x. We just multiply it by this way. Okay. Then 9 4 the 36 minus 9x is equals to 15x. Then 36 is equals to 15 plus 9x. So it will be 36 is equals to 24x. Then 24 come here. So 36 divided by 24 is equals to x. Then x will be 1.5. So distance from here to here is 1.5. When it is 1.5, then it will be 4 minus x. 4 minus 1.5, it will be 2.5. Okay. Now, why we need this distance? Because we have to know the area under the shear force diagram. So here we have the triangular body. The area under the shear force diagram will be 1.5 times 9 into half. Okay. 1.5 times into 9 into half. Okay. So area under the shear force diagram is half AB. So half, because it is a triangle, so half A is 1.5, B is 9. Okay. So it will be 0.5 into 1.5 into 9. It is 6.75. 6.75. It is positive because this body is in the positive zone. Okay, so we start from 0. So it is in the positive zone and it is in the second degree curve because it's a UDL load. So it will be from here to here, it is 6.75. Okay. After that, we have to know the area of this triangle, which is subtracted from 6.75. So what is the area of this triangle? It will be half 2.5 into 15. Here we have the value of 15. Okay. So it will be 0.5 into 2.5 into 15. So it will be 18.75. So area of this. So 6.75 minus 18.75. It will be minus 12. So it will be minus 12. Minus 12. Then we have to add the area of this triangle. This triangle. What is the area of this triangle? Half time 2 times 12. Area of this triangle is half time 2 times 12. So it will be 12. So minus 12, this is positive body. So it is positive 12, minus 12, positive 12 will be 0. Okay. So this is positive zone and this is negative zone. So this is our bending moment diagram for this figure. Okay. So this is the end of the session. Hope it is easy. So see you inshallah in the next lecture.